Welcome. As you can see at your screen, there is one more simple problem to solve. And yes, you can see the problem. This is nothing. This problem is like this. People usually solve this problem. There is a rough surface, flat surface, and a wheel or some kind of rolling body is left to slide first, rolls bit slipping first, and then it ultimately starts rolling, and then we find something like find the velocity of this rolling body at the moment when it started rolling, the time taken after which it started rolling, and this kind of problem people usually solve. I didn't do anything, but I just changed this problem in this manner. That means if the motion is taking place on a same surface, but the surface against which this rolling body is moving, is rough and its shape is circular. As you can see in your problem, it is given a cylindrical hoop. I guess this hoop should be solid. Okay, it may be solid or hollow, I don't know. I will solve by putting moment of inertia. I will regard something in my mind. Hope you don't need to worry about. It's a rolling body, round body. A cylindrical hoop of radius r equals 3 cm touches the edges of a smooth horizontal surface. Horizontal surface is smooth, but this circular thing is not smooth. I want to tell you, you are doing all these experiments on a table. So table is just smooth, but on the table you put a circular barrier like this, and that barrier is rough. So edge of a smooth horizontal surface shaped as a circle. Okay. With radius r, the statement is a bit confusing. With radius r equals 10 meter, the hoop is given a velocity given a speed of v0 equals 30 meter per second. Its initial speed is given. It has got only the linear velocity. Only you can see here that only linear velocity to the center of this hoop is provided, and there is no angular velocity. This is not rolling at all. Initially it has got only linear velocity, so omega is 0 initially. The coefficient of friction between the between the edge and the hoop, this thing is called, I'm calling it, is an edge, nothing else, is mu equals 0.1. And determine the modulus of the hoop's speed vk. VK is sitting here next to me, so I named this problem. I named him in this problem as VK after slipping between the edge and the hoop siege edge. That means slipping siege edge, not the rolling. That means now the rolling without slipping starts, and as well as the time interval tk after which this will occur. This is a problem, interesting problem. Found it interesting. So you can see I set up a coordinate system. This time this is a different coordinate system. The origin is here at the origin, not the origin. Forget about the coordinate system. I haven't set up it, I guess. So this is the normal direction and this is the tangent direction. You are not going to worry about this is some kind of new forces acting on this hoop or something. They are not. These are just directions. One is normal and another is tangential, and we are going to write the equation of motion of the center of mass of this hoop in projections onto the normal and tangential axis. That is why it is mentioned in this figure. And you can see the free body diagram of this hoop here. The forces acting on it are normal force. Of course, the motion is taking place in bird horizontal planes, so we don't need to worry about role of gravity. It has nothing to do with anything. So I have not shown it. And the friction force you can see here. This is the kinetic friction. So if it is slipping in this manner, its velocity is in this direction, then this velocity is is it in along the positive direction of positive tangential direction, then friction must be opposing its velocity. Because it's sliding friction, it is opposing sliding, so it will be here, like you can see. And what next? So this thing, our hoop, is acted upon by normal reaction force and the friction force from the edge. Yeah, of course. And well, let us write the equation of motion of the center of mass of the hoop. And in selected normal and tangential along this normal and tangential axis, and I assume that a certain moment of time, I haven't assumed anything else about this time. I haven't set up this time for a particular moment, particular event, but at some moment of time, its velocity is v, you can see here. And then I'm going to write its equation of motion of its center of mass. The equation of motion of its center of mass, it's my habit, along the normal and tangential axis. And I can write here, normally acting along the normal itself, so I can write here n is equal to mass into normal acceleration. This is my equation 1. And the tangential axis is taken along this axis, and the friction force acting in opposite direction to the taken axis. So I'm going to bring my mathematical morality here, and I am going to write minus F is equal to mass into acceleration along the tangential direction. So it's all normal, and you can see normal and tangential acceleration. Sorry. I can also write here normal acceleration can be written as v square by r. That is not r in this case. That will be, speed is v, but it's the radius in which its center of mass is moving in a circle is r minus r. Capital R minus r. Capital R is the radius of the circular edge, and r is the radius of the small r. So normal acceleration can be written as like this, and tangential acceleration is simply dv by dt. So this is the equation set 3. And now I'm going to write the equation of moments, because it's also rotating. So I'm going to write a torque equation about an axis passing through. Axis is shown here, axis passing through its center of mass. It's safe here, center of mass. So I don't need to worry about instantaneous center, although I know it is not I'm not sure about its instantaneous center of rotation, so I'm not going to take any extra burden to find the instantaneous center of rotation. And I know for sure that this is not the instantaneous center of rotation at the moment, because this is slipping, not slipping is not absent. So I'm not going in a trap of instantaneous center of rotation. So I'm going to use center of mass safely, and I can see from this center of mass there is not much problem, because only friction force is producing a torque, and friction force is producing a torque in this direction, clockwise direction. So the axis you can see here, the cross mark, you can see that the axis of rotation is also passing through its center of mass and taken into the plane of the paper. So and the friction is producing a torque in the same direction. So I can write the torque equation as F multiplied by R equal to moment of inertia about its axis of rotation, that is I naught, and d omega by dt, angular acceleration, d omega by dt, beta, anything you write. And I guess if I take this I naught equal to mr square by 2, that means this is something solid hoop. So fine, I took just at will. Now I know for sure if this thing is slipping, and I know it's slipping because we don't see any angular velocity at the initial moment. It was simply translating, so it is bound to slip, because having v, the velocity of the center of mass, and not having omega, it causes slipping. So it was slipping. So now slipping means friction force is equal to mu1. Yeah, I know, sliding friction. And when this slipping ceases, we know there will be a relation between velocity of the center of the hoop and its angular velocity, and that is going to be v equals r omega. So I'm going to need v and omega also. But before that, we have this thing. The guiding principle is this: F is here, the friction force is here, kinetic, and it is equal to mu. And so how should I manipulate this? I can write here something. F is minus m tangential acceleration, that is simply dv by dt, or dv by dt, nothing else, equals mu n. N is m normal acceleration, that is v square by r minus 1, r minus r. And so you can see here we got a equation like dv by dt equals minus mu v square divided by r minus r. And so this is a first degree, first order variable separable differential equation, and I'm going to separate the variables and integrate it. And this is nothing but dv by v square, and its initial velocity was given perhaps v naught, and at any time t its velocity is v. So I'm going to put on the limits, and it is equal to minus mu divided by r minus r and dt. Then the time starts from 0 and it is any time t. So we can get the velocity in terms of time. Velocity is a function of time, and I got it earlier. Bt is nothing but v naught r minus r divided by r minus r plus v naught mu t. This is the velocity at any time t when the hoop is slipping. And now we need to find out omega separately, because there is no v equals omega r right now because it is slipping. So where can I find the value of omega? Where was the omega equation? Where was it? Oh, this is it. This is the omega equation. F you can write here as mu n. F you can write here as mu n, and put mu n and n equals this, and then you can get your omega. And I naught, also use I naught. So I'm going to use all those things, and I'm going to write what? F equals mu n. N is what? N is m a n, and a n is this. So I'm going to write down mu F equals mu n, and n is m v square by r minus r. Mu n, yeah, that's right, multiplied by r equal to what? m equal to mu naught. No, equal to I naught. I naught is mr square by 2 omega. Not omega, that was I alpha, I d omega by dt. Yeah, this was I naught mr square by 2 d omega by dt. Right. Right. So I got here d omega by dt equals 2 mu v square, 2 mu v square upon r multiplied by r minus 1, or this is d omega by dt. So I can find omega as a function of t as twice mu, and I can put v is here, and a square, that means I get v naught square r minus r square, r minus r square divided by the whole thing is going under integration. That means dt multiplied by r minus r plus v naught mu t square, and 0 to t. Omega initially was 0, so I simply wrote down here omega t and nothing else. And this is simple integration, simplest, or a plus bx, nothing. It's simplest. A square it is, so there is no chance of log. You can put everything equal to z and you will get your result immediately, and you will get omega t as well, and this will be nothing but 2 v naught square mu t divided by r r minus r plus v naught mu t. Again, omega in terms of time, you will get something like that. And v and omega, you found out your v and omega, go and put there v equals omega into r when the rolling starts, when the slipping ceases, and you will get the value of r, value of time, volume of value of time. And I got earlier, this is still in my hand, this will be, you are going to get r minus r by 2 mu v naught, and something like that. If you want to get the value of v at that moment when the rolling begins, its value vk was 2 by 3 v naught, and if you wish, you can put the values, all the values are given, and you get your numerical values. The method I was displaying is this. I guess I am getting bored of solving these simple problems, so I will take few interesting problems in next few videos. Thank you very much for watching.